Okay, Assalamualaikum. Good morning, everyone. Okay, so we continue our class. Okay, so suppose we should have a feedback, but for some reason we have to move to the online. So I hope that by tomorrow we can physically. Okay, only for today we have class. Right. So how's everyone? I hope you I think everyone is in the campus, right? Okay. So hopefully the water issue problem or supply already been solved gradually. Okay. So that you have water supply in your campus. Okay. Um, okay, so for this week, okay, I'm planning to start with the new chapter. Okay, even though this is not part of your test, but I believe this some of the example or exercise for this chapter is a good is a good way to make it some exercise related to your test one, because some of the exercise is using the same approach, like how to define the table properties, how to define the properties, how to calculate the properties based on the given other properties, intensive properties. Okay, I'm not sure whether I have upload this slide or not. This chapter 4. I hope I already uploaded. But if not, please remind me at the groups, okay? Because I think I already upload for both section. But if I not upload yet, please update me so that I can upload the slide relevant to this chapter. Okay, right. So for this chapter 4, okay, we will start the energy analysis of the closed system. Okay. Um, so like I say, in the chapter 3, in the last week, we have discussed on the energy and energy transfer. Okay. So how the energy defined for a system. Okay. Energy can be defined based on the internal energy, with the potential energy and the kinetic energy. But if energy are considered is have some mass in and mass out, so you have additional energy which is include the flow of energy. Okay, and this energy of the system can be transferred either by heat or work. Okay, or sometime for the open system we can consider also the energy due to the mass flow in and out, if we are dealing with the mass flow in and out. But for the chapter 4, we only focus on the closed system. Okay, so closed system, when we talk about the closed system, okay, let's say we have this closed system. So we know that uh, for the closed system there is energy in and out. Okay, energy can transfer from the system to the surrounding or vice versa. Okay, but for the mass, okay, so you cannot transfer mass flow in and out, because there is no way to transfer the mass in and out for a closed system. So for the energy, yes. For the mass, no. Okay, so that is the definition that you are using in the first chapter. Okay, the definition that you are using for the closed system. Okay. So what we will cover in this chapter, okay, first we will look into the definition of boundary works. Okay, this one, boundary works. I think if you recall back in the chapter 3, we have covered several type of work. Okay, type of work. If you still remember in the chapter 3, we learned about the um, electrical work. Okay, we learned about spring work. Okay, we also discuss about the shaft work. Okay, which may be related to the pedal wheel or to the propeller. Okay, uh, also we have the boundary work. Okay, so um, we have discussed several works, but we not really discuss the boundary work. Okay, so the boundary work will be discussed uh, quite a lot in this chapter, in this chapter 4, because the boundary work is related to the uh, moving boundary, related to the moving boundary. Okay, because if you if you realize in the closed system, there is some system that has a capability of moving the boundary, like a piston cylinder. Okay, like a piston and cylinder, you have the boundary that can move upward and downward. Okay, so this works. Okay, whether you are going up or whether the piston going down. Okay, related to the boundary works. Okay, so how the boundary works can be produced, it's depending on the how the process inside of the closed system, whether it is related to the heating, whether it is related to the cooling, whether it is related to the expansion, whether it is related to the compression. Okay, so this is several process related to the boundary works, because this boundary works is commonly, okay, used in the thermal device like reciprocating device, okay, such as the automotive engine and the compressor. Okay, so that's why we need to learn more detail about the boundary works. Okay, and then once we understand the boundary works, we can apply the first law of thermodynamic, okay, in order to calculate the energy balance or energy principle, conservation of energy principle, okay, known also as a energy balance. Okay, so from the conservation of energy principle, we used to develop the general energy balance, and then we do the energy analysis of the closed system. Okay, and then after we identify or we understand the energy balance, there is some cases that we need to use the terms of specific heat. Okay, whether at the constant volume or constant pressure, because this information of the specific heat related to the calculation of the energy enthalpy of ideal gas. Okay, so in other words, first we learn about the boundary works. Second, we use the energy balance to solve the energy analysis of the closed system. And the third one, we use the information of the specific heat, okay, in order to solve the ideal gas problem, okay, a problem that using ideal gas as a working fluid. Okay. So once we know this, so we can solve any problems related to the closed system using the energy balance. Okay. Whether it is related to the heat or works interaction for the pure substance, either water or refrigerant, as well as the ideal gases or incompressible substance. Um, this one incompressible. I think this is related to the solid, but we not really cover in detail. We only cover about the pure substance, this one, and ideal gas. Okay, incompressible substance is just for your knowledge only. Okay, so that is the objective of the chapter 4. Okay, so first we look into the boundary works. So what is the boundary work? Okay, so boundary works, like I say, is basically works that produced by the boundary. Okay, so this is a piston cylinder. Okay, so this is a piston cylinder. So the piston cylinder, uh, normally we can relate to the a process of um, moving upward or moving downward. And this moving upward and downward related to the process of the expansion and compression. So normally when we are talking about piston moving upward, so it is related to the expansion. Why? Because the volume increase. Okay. And for the piston going downward, it is related to the compression because the volume reduce. Okay. So you can say here volume increase, here a volume reduce or decrease. Okay. So that is the two general definition or two general condition for the boundary works. Okay. So either the piston going moving upward. Okay. So upward direction related to the expansion, volume increase, or downward. The piston moving downward related to the compression and the volume reduce. Okay. So how we can calculate the boundary works? So we use the basic calculation of force time distance. Okay. So any works we can calculate if we know the force and we know the distance. Okay. F times X works. Okay. So if the force is a constant, while the distance is changing from one point to another point, so we can calculate the total boundary works. Okay. Can be calculated as long as you know the force and the distance direction from point zero to the point one or point final, one or two or zero to one. Okay. And from this equation, you can represent the force. Okay. You know that pressure equal to force divided by A. Okay. So force equals to P times A. Okay. So that's why you got these terms. Okay. And because of P represent the pressure inside the so P is basically the pressure inside the cylinder, okay, or the piston cylinder. Okay. A is the cross section and ds is the how far the movement of the piston. So we can relate the A ds to the volume. Okay. So PdV. So from the FDS, we can rephrase because, like I say, in the thermodynamic, we don't really use force. we more likely to use a pressure. There is no properties of force related to the working fluid. So, but we have a lot of pressure information compared to the force information. So that's why we need to uh, what happened? Uh, is it okay now?
Okay.
Okay. So you can see my slide clearly, okay? All right. So we need to use pressure more frequently than the force. So the boundary work calculation will become PDV. Okay. So to calculate the boundary works, we can use the integration of PDV. Okay, where P is a pressure, uh, dV is a change of the volume from the initial to the final condition. Okay, so that's why regardless of any system, we can use this boundary works. Okay, whether it is a piston cylinder, whether it is a rigid tank, as long as a closed system, we can use a PDV calculation. Okay, where P is represent the pressure, dV is represent the change in the volume. Okay, to calculate the boundary works. Okay, so before we go to the type of the process, we need to understand, because of we have the expansion and the compression uh, condition. Okay, we need to take into account that for the expansion, the boundary work will be always positive. Okay, so expansion related to the boundary work positive, while compression related to the boundary work which is in negative value. Okay, or if you can write as well like this: V boundary for expansion will be always positive. Boundary works due to the compression will be always negative. Okay, so you also can write like this. Okay, because at the beginning we discussed that normally we only have two condition. One is expansion, one is a compression. So sometime when you have the expansion, you know that your boundary work will be become positive. Okay, if you got the boundary works on compression, you will get the negative. Okay, okay, next okay, we looks also the thermodynamic diagram related to the boundary works. Okay, so since we need to calculate boundary works equals to integration of PDV, so that's why this equation related to the area under the graph, under the graph of PV. Okay, so that's why if you recall back in the chapter 2, we always ask you to plot PV diagram and TV diagram. Okay, so why? Because of PV diagram, if you plot a PV diagram, the area under the graph will be used to define the boundary work. Okay, TV we will look into later. Okay, generally TV will be related to the heat generally, but not specifically TV. Okay, if you want to know more details, normally for the, okay, if this is for boundary works, which is works for the Q, it is related to the TS. Okay, temperature. entropy diagram. Okay, so if W related to the PV, Q related to the TS. But in order to understand the TS, you need to understand the TV first, TV diagram. Okay, so that's why the reason why you learn the PV diagram, because the PV diagram will assist you how to draw the process from one point to another point like this, from one point to another point, from the initial to the final, and then the area under the graph is represent the boundary work. Okay, so that is the reason uh, why you are asking to understand the PV diagram. Okay, because the knowledge of the PV diagram will reflect to the boundary works calculation or boundary work definition. Okay, so this PV diagram will be used to identify the process involved. Okay, so like this, okay, to calculate the boundary works, you have the uh, calculation of the area under the graph, which is a PDV. And in order to calculate the area, you need to understand the process. So here there is a three type of process. Okay, A, B, and C. Even though you can see the A, B, C have the same initial point and the final point, but the process have slightly different. Okay, where A represent the boundary works of 10 kilojoule, B represent 8 kilojoule, while C represent 5 kilojoule. So basically, you can indicate this area or the value of boundary work by the area under the graph. So this is WC, okay, and this is for the WB, okay, and this is for the uh, WA. So the area under the graph have some different value, magnitude, which reflect the type of the process from the initial to the final condition. Okay. Um, okay, if you have the okay, that is for the first diagram. For the second diagram, this is the first diagram. For the second diagram here, so any process, okay, which has the same initial and the final stage like this. First, you have the process from 1 to 2, which is in the process B, and then from 2 to 1, which is process A. So meaning that work net is equals to the W12 plus W21. Okay, basically W12, because 12 is volume is reduced, so basically negative 12 plus W21. Okay, why negative here? Because the volume reduced. So that's why I put negative here, because it is related to the compression. Why 2 to 1 is positive? Because it is related to the compression, expansion. So this will equals to the area within the process, okay, which is W net. Okay, so this is related to the process in a cycle. Okay, so if the process occur in a cycle, then you have to find the the net, the total between the work W12 and W21. Okay. Okay, so that is the some condition that you might use if you have more than one process. Okay, now we need to understand what kind of process. Okay, what type of the process. Okay, so in the early chapter 1, we learned about several process which is known as a isochoric, okay, constant volume, isobaric, constant pressure, isothermal. Okay, so which is we know that this is a V constant, pressure constant, constant temperature. Okay, so you know that under constant volumes, there is no change in the volume. Under constant pressure, there is no change in the pressure. And the constant temperature, there is no change in the temperature. But if there is none of the volume or pressure or temperature is not constant, so this is the the remaining. If the volume is not constant, if pressure is not constant or temperature not constant, so all these represent the polytropic process. Okay, where you need to identify there is a change in the volume, there is a change of the pressure, and there is change of the temperature. So if generally, if I can say, most of the process in the real problem is fall under the polytropic. But to simplify the process, we can assume some other parameter constant like volume or pressure or temperature. So this is the four common thermodynamic processes that you might be dealing in this chapter. Okay, constant volume, constant pressure, constant temperature, and polytropic. Okay, before we go to this equation, okay, remember general equation for boundary work. So we need to define the boundary work for each process. Uh, the general equation is integration of PdV. Okay, so we need to find what is the boundary work for the constant volume. What is the boundary work for the constant pressure? What is the boundary works for the constant temperature? And what is the boundary work for the polytropic? So we need to define four boundary works based on the general equation of PDV or integration of PDV. Okay? Okay. So, okay, this is some example of the final calculation. Okay. I think we before we go here, we can discuss from this table. Okay. So if you have the relation of boundary works PdV for the first constant volume, if the volume is constant, what happened to the boundary works? So there is V is constant. Sorry, we go zero. V is constant, meaning dV will be zero. Okay, when V is constant, dV is zero. So if dV is zero, so boundary works for the constant volume will become zero. So that is the first equation for the boundary works under constant volume. That's why for the boundary works for constant volume, the value will be zero. Okay. Second is pressure constant. So we can do some derivation. Okay, boundary works PdV. Okay, we know that pressure is a constant. So because of pressure is constant, we can bring the constant value out from the integration. Okay, so boundary works PdV. So since the change only dealing with the volume, so boundary works can be calculated if we know the changes V2 divided by V1. Okay, integration of dV. So here the boundary works for the constant pressure P V2 minus V1. Okay, so how about this constant temperature? So again, you are using the integration, but this time we need to use the relation of P dV. Okay, okay. You look here under the constant temperature, the relation of PV will become PV equals to C. Okay, if you look here, under constant volume, V is constant. Under constant pressure, P is constant. Under constant temperature, PV is constant. Okay, how they got this is basically using PV-MRT relation. Okay, so if this is the constant, R is constant, M is also constant for the closed system. So PV equals to C. So that's why you got this relation, PV constant. Okay, so using WB integration PdV and PV equals to C, which is P equals to C over V. So you combine this equation with the integration, meaning here you get C over V dV, meaning here C is constant, so you bring outside 1 over V dV. Okay, you do the integration and you finally you will get like this one. Okay, where is, yeah, this one, T constant isothermal. Okay, PV ln V2 divided by V1. Okay, so this is P constant isobaric. Okay, this is for the polytropic. Okay, so basically you have this equation for polytropic. You got the PV ln V2 divided by 1 for the isothermal, and you got P V2 minus V1. So where is the other one? Oh, constant volume. For the V constant, the WB equals to 0. So you got 4. This is 1, this is 2, this is 3, this is 4. So uh, the longer equation, of course, related to the polytropic. Okay, so you can see how the polytropics, because the polytropic using equation of P equal, okay, PV equals N equals to C. So you change to the P equals to C over Vn. So using this, you put into the integration of PdV, and finally you have this equation. You don't need to remember. this equation. Normally, the equation is given, or sometimes you can understand from the derivation from the PDV with the PV relation. Okay, so if I can put some summary here. So for the constant volume, the volume for the constant process is 0. For the constant pressure, the boundary works is a P times the change in the volume. And for the constant temperature, PV ln V2 divided by V1. Basically, you can rearrange this with other terms, okay? Like here, they don't put 102, but so you can use either P1 V1 ln V2 divided by V1 also equals to P2 V2, okay, ln V2 divided by V1, okay, because this PV can be 1 1 or can be 2 2, but you cannot mix between 1 and 2 for the pressure and volume, okay. Like here, why they put P0? Because P0 is equals to P1 is equals to P2. Okay, so there is no change in the pressure. Okay, so what is 1 and 2? 1 is normally representing the initial state or initial point. 2 represent the final state or final point. Okay, and lastly, for the polytropic, you have PV, P2, V2. Okay, this is a bit a long length equation. P2 V2 minus P1 V1 divided by 1 minus N. So what is N? N is a polytropic index. N is a polytropic index. Normally, it can be given in a problem, or you can find from the calculation. Okay, and you know that PV equals to MRT. So you can replace the PV term with the MRT term. So that's why you can use this two equation. Okay. If you don't have the PV but you have the T value, then you can use the terms of MRT2 minus MRT1. Okay. How to find N? Okay, let's say the N is not given. So you know that PVN equals to C. So P1V1N equals to P2V2N. So basically you can solve this, or you can find N if you know all information of P1, V1, P2, and V2. So P1 over P2 equals to V2 divided by V1 to the power of N. Okay, so it's like some mathematics equation, rearrange the equation, but generally how you got this is from the knowledge of the ideal gas equation, okay, and also from the basic definition of boundary works. Okay, so this is the 4 process that you need to understand in order to calculate the boundary works. Okay, any question? If not, we go to example. Okay, first example is for the constant volume process. I don't think we have a time to cover all, but we try to do 1 or 2 exercises today. Okay. Okay, so this example is from the textbook. So basically, here you have a rigid tank. Okay, contains air at 500 kilopascal and 150 degrees Celsius. Okay, so initially the pressure is at 500 kilopascal and temperature 150 degrees Celsius. As a result of heat transfer, the temperature and pressure inside the tank drop to 65 degree and 400 kilopascal. So that means from 1 to 2, so there is some heat transfer, okay, which make the pressure drop to 400 kilopascal and T2 become 65 degrees Celsius. So seems that there is a reduction of the temperature. So you can say it is related to the cooling process. Okay, heat transfer, and from the heat transfer, from the temperature value, the temperature is dropping to 65 degrees Celsius. So you can say it is a cooling process. Okay, but because of this is a rigid tank, okay, so the rigid tanks meanings the volume is constant, no change in the volume. Okay, so determine the boundary works done during this process. So boundary works, okay, PDV is equals to 0 because of no change in volume. Okay, because the this is a rigid tank due to rigid tank. Okay, so so you don't need to solve the problem, even though the information given on the about the pressure and temperature. So because of the rigid, the volume is not changing, and because of that volume constant, so the boundary works will be 0. Okay, so that is the first exercise, which is a bit simple. So if you are dealing with any rigid container, rigid tank, rigid section, rigid box, okay, so if they ask you to find the boundary works, or if any system, let's say you have the piston cylinder, but the piston is not moving, so you can say there is no boundary works. The boundary work will be equals to 0. Okay, next one. This is a bit longer. Uh, okay. Boundary work for concept. Okay, forget about the title. Okay, because normally for the problem we don't know what the process. We just look into the information given. A frictionless piston cylinder device. Okay, or piston cylinder device. So when we talk about piston cylinder device, we know that one of the boundary is moving. Okay, contains 5 kilogram of steam at 400 kilopascal and 200 degrees Celsius. So basically, this is a piston cylinder device, and then the working fluid is a steam, which is you know that this is a water. Okay, so this is a water as your working fluid. So you need to define the properties of water. Okay, so initially the information given, mass 1 equals to 5 kilogram, pressure 1 equals to 400 kilopascal, and temperature 1 equals to 200 degrees Celsius. So that is the initial information or initial state of the steam. Okay, so you can see here the pure substance or the working fluid is a water. So you need to find the table of water. Okay, heat is now transferred to the steam. You can see the heat is transferred to the steam. So you can see uh, the temperature now is become increase. Okay, the temperature increase. So basically, it's a heating process. Okay, and you know that uh, because of the piston is not fixed, so the piston can move. Okay, that's why here they put if the piston is not attached to a shaft, meaning the piston is freely moving. Okay, if the piston is attached to the shaft, meaning the piston is some constraint to move upward or downward. Okay, and mass is constant. Okay, so piston is freely move. Piston is freely move. So when the piston is freely moved, this is related to the process where the pressure is a constant. So in other words, you can say P2 equals to P1. Okay, and here mass is also constant. So you can see mass 2 equals to mass 1, which is this is related to the closed system. So as a closed system, the mass will be equal. For P2 equal, this is equals to the isobaric process. Okay, determine the work done by the steam. Okay, so work done by steam is only due to the boundary work. Okay, because the steam, because this when you hit the steam is become energetic, become there is a lot of energy inside, and they try to expand. They try to create some reaction due to the heating. Okay, so the piston is moving upward, uh, and the temperature is increased. Okay, so the boundary works is by the uh, pressure constant process. Okay, which is WB, and this can be calculated PV2 minus V1. Okay, and how to find the V2 and V1? So you need to find the from the table properties. You cannot, okay, some might say that, okay, I can use PVMRT, okay, because PVMRT, we we have the T here, we can find R from the table, we have the mass here, we have the pressure, so we can find the V. Okay, so can we use this equation? Yes or no? Can we use PVMRTs to solve this problem? Okay. Okay, thank you, Irfan Zairi. So, yes, the answer is no. Because our working fluid is water. It's not a gas. If gas, yes. If water, no. So to solve this, we need to use a table. Okay. So if if we can so back to the original equation, okay. Boundary works equals to P V2 minus V1. Okay. Um, so we need to find the specific volume because we know that V equals to the specific volume multiplied by mass. Okay. So V2 equals to specific volume to find multiplied by mass 2. V1 equals to specific volume 1 divided by mass 1. We have the mass. but we don't have the specific volume 2 and 1. So basically, we need to find the uh, need to find V1 and specific volume 2. Okay, so we start one by one. Okay, first we have the pressure at 400 and temperature 200. Okay, so find specific volume 1. Okay, given 200 kilopascal for the P1 and T1 is a two how much 200, sorry, 400 kilopascal. Temperature is 200. 400 kilopascal for the pressure. T1 is 200 degrees Celsius. Okay, how to find V1? So same like previously, find the phase first. Find the phase 1 first. Okay, because we don't know which table we want to refer. Do we need to refer to the saturated table, or we need to refer to the superheated, or we need to refer to the compressed liquid? So first we need to find the phase. Okay, given two information, pressure and temperature, so you can choose either one. So normally, like I say, I prefer to take the pressure and find the temperature of the saturation. So at 400 kilopascal, find TS. Okay, what is TS at 400 kilopascal? Can someone check from the table? You go to the 400 kilopascal table. This is table A5. So table A5. Okay, thank you, Zairi. So at 400 kilopascal, Ts equals to 143.61 degrees Celsius. Table A5. Okay. So for those who are not fine, so make sure you know how to get 143.1. I also compare to check the value. Okay, so at 400 kilopascal, you have 143.61 degrees Celsius. Okay, correct. Okay, so then what do? You compare T1 uh, versus T saturation. Okay, compare T1 with T saturation. So you can see that T1 is 200. T1 is greater than T saturation at 400 kilopascal. Okay, because T saturation is 143, T1 is 200. This is 143. So you can see that state 1 is greater than saturation. So phase 1 is basically super vapor. Okay, like I say, you are using the same approach, the same technique that you are doing exercise in the chapter 2. Okay, so superheated vapor. So once you know superheated vapor, what is the V1? So V1 is V at superheated when pressure is a 400 kilopascal and T equals to 200 degrees Celsius. So you can find from the table A6, okay, the value of pressure 0.4 megapascal, because it is equivalent to 400 kilopascal, and temperature 200 degrees Celsius. Okay, so you open table A6, 0.4 megapascal, temperature 200. So the corresponding value of specific volume, how much? 0.474, 474.88. Uh, I think that is not for 200. Zoiri. That one is for the 150. Um, it should be 200. Just a line below the 470, 200. Right. It's okay. No worries. At least you try. I don't know the rest. I hope okay, you can check um, with your own tables or with your own properties. Uh, can you type again, Zairi, the right one? So the V1 equals to 0.5, okay, thank you, 3434 meter cube per kilogram. Okay, so that is a V1. Okay, so from the phase, you know the superheated vapor, and from the given pressure and temperature, you find the corresponding properties of specific volume 1. Right, so that is a V1. So how about V2? So we repeat the same process. Okay, so for V2, find the V2 given pressure 2 is equals to P1, which is at same 400 kilopascal, but T2 is now become 250 degrees Celsius. So you use same approach again. Okay, so you need to find the phase 2 first. Okay, so at 400 kilopascal, find T saturation. And you know that T saturation is 143 because they're the same value, right? 143.61 degrees Celsius. Okay. So, and then we compare, okay, compare the T2 versus T saturation. Okay. We know that T2 is greater than T saturation at 400 kilopascal. So from this, it's again the phase 2 is a superheated vapor. Okay, superheated vapor. So if the superheated vapor, so we are using the same approach. So V2 is equals to V at superheated at 400 kilopascal and 250 degrees Celsius. So you can find the V2 directly from the 0.4 megapascal and 250 degrees Celsius table A6. Okay. So what is the value? 0. Okay, thank you, Zai. 0.595 to 0 meter cube per kilogram. Okay, so that is your answer for the V2. So Once you get a V2, you can back to the original boundary work. So therefore, the boundary work by the steam equals to P V2 minus P V1. Okay, so you know that V equals to M times volume. Okay, so you know this. So the equation become P M2 V2 minus M1 V1. And you know that M2 equals to M1, and you can bring the M to the out to the out from the bracket, V2 minus V1. Okay, so you write again, what is the M? What is the M just now? 5 kilogram. Okay, 5 kilogram, pressure 400 kilopascal, V2 is 0.59520 minus V1 uh, 0.54, sorry, 53, 53434. Okay, 53434. So you minus the value and then multiply by 5 to 400. And this is kilo, this is a kilopascal. This is a meter cube per kilogram. Kilogram cancel kilogram. So finally you will get in kilojoule. How much? Can someone calculate this? 59520 minus 534, 0.53434, 1 kilopascal. 116,320. Okay, kilojoule. Is there any answer there? 122 kilojoule. This is 400 116 or 11. How come you got uh, how come you got 116320, Irfan? So I really, okay, that is more closer. 1 to 2.4 kilojoule. Let me check. You don't need to multiply by a kilo. Okay, okay. Never mind. Okay, thanks, Irfan, for trying. Okay, multiply by 400, multiply by 5. Okay, 1 to 2. So this is wrong. What is the so 1 to 2.4 kilojoule. Okay, so that is the boundary work for the process of heating of the water under constant pressure process. Any question? So basically, if you look to the original problem, the process is heating of the water from one state to another state, which creating some energy transfer in terms of heat, and this energy transfer creating some movement of the piston from the one position to the next position, which is related to the expansion. Okay, logically, when you heat the water, what happened to the water inside of the container? So there will be some reaction which is related to the expansion. Okay, normally heating, when you heating any fluid, so the fluid will try to expand. Okay, whether it is water or gas or refrigerant, the the fluid will try to expand. So basically, the volume is increased and creating some a temperature increment. Okay, for this particular process. So how to calculate the movement of the piston due to the boundary work is using this equation PdV, or for the constant pressure, P multiplied by change in the volume. Okay. Of course, you don't get the volume directly, but from the table properties, you get the specific volume, and then you multiply by mass in order to get the volume. And finally, you multiply the change in the volume with the pressure, and you can get the equivalent boundary work for this particular process. Okay, so that is a constant pressure process. Okay, the next example is a constant temperature. I think this one. Oh, okay, this one is air. I don't plan to discuss this. I plan to discuss this example tomorrow in class. Okay, hopefully. Um, can we make it tomorrow class as a physical? Is there any problem for you to come to the class? Or some of you are in your hometown? I don't think some of you going back to your hometown just because of the water supply problem. Okay. Oh, vote. Okay. Okay. Later, I will try. I will put some vote for the class. Hopefully, we can have a class tomorrow physically, because from there we can do the exercise more understand. Okay. But if you look to this example, the the working fluid now is air. Okay. So we might not use the table properties. We need to use the PV MRT. Okay. So for air, we need to use a PV get ideal gas equation, PV MRT, to solve this problem. Okay. And I think the next one we have another example of uh, very slow, polytropic. Okay. This is for the next example. All right. Okay. Any question so far? So we have done um, the process for the constant volume, and we have done some exercise for the constant pressure. So the remaining constant temperature and polytropic, we will discuss in the next class. Okay. So if there is no question, I think that's all for today. I'm not planning to do the class for 2 hours. Okay. Hopefully we can continue uh, for the remaining exercise for the tomorrow. Okay, let me open why my mouse is not working. Okay, sorry. Um, okay, can you wait for a while I'm opening the page of the attendance? Okay, so that is the QR code. Uh, can you scan the QR code? Why is not appear? It's not working, is it? Why I cannot see your name there? Yes, one QR for two section. For this is for section 5, but for section 6, your name will be appear as well. I think so. Uh, why? For the section 6, you cannot scan, is it? Yes, we can. You can, right? Okay. I will check from the. Okay. So if you're done, okay, that's all for today. Thank you very much. Hopefully we can continue tomorrow class uh, in the physical class tomorrow. Okay, if everyone vote for the physical. Okay, guys. Thank you and see you again tomorrow morning. Okay. Assalamualaikum and salam sejahtera.